Okay, today's lesson is 4-3 concavity and points of inflection. So now we're going to learn about what does the second derivative tell us about the function. So I'm just going to read through these super quick because you can do it on your own. One thing we know when a graph is concave up, what we have right here, the tangent lines are below the curve. When it's concave down, oh great, my markers aren't working well, then the tangent lines are above the graph. So in essence, the thing you need to remember with concavity is your smiley faces. When the second derivative is positive, you're smiling. So that means you're concave up. When your second derivative, wherever it's negative, that means you're frowning, so you're concave down. So if we look at the cubic function right here, we want to look at where is this positive, where is it negative. Okay, so if I look right here, this piece of the graph is frowning. This piece is smiling. So here is concave down, there is concave up. So I know it is concave, so then this is how I write it, con up from negative infinity to 0, and it's con down from 0 to infinity. And wherever it changes concavity, that is what we call a point of inflection. So right there at 0, 0 would be my point of inflection. So we'll talk about a little later on how to find it using calculus, but you can look at the original function and determine concavity as well. And we're going to practice a little more of that on the next graph. So we want to look at on which intervals is the graph concave up, and on, so number 1, we're looking for that smiley face. And I wish I had colors, but I don't. So right here, it's up, up, up. So we would say from, -2 to -1, and from 1 to 3, and then from 4 to 5. That's where we're concave up. Now we want the intervals where we're concave down, so we're looking for that frowny face. So my first one is from -1 to 1. Well, right there, nothing's going on there. That's linear. There's no concavity there whatsoever. Then my last one is right there from 5 to 6. Intervals where there's no concavity, well, we just identified that 5 to 4 because that's linear. Wait, I don't know why I said from 5 to 4. 3 to 4. And if you notice right here, 6 to 7, kind of hard to see, but that is also just a horizontal line. So from 6 to 7, there is no concavity there. So now we want to identify points of inflection, and that's wherever it changes from concave up to concave down. So right there, because I went from smiling to frowny, now I'm going from frowny to smiley. So there's another one. What about this one? Can that be a point of inflection? It won't, because we just identified that didn't have any concavity to it, so we skip that one. Then our next one would be right there, because we go from smiling to frowny. So the points of inflection would be at -1, 1, +1, 1, and 5, 1. Okay, so now we're going to practice. Well, what if I just have the equations and I don't have time to look at the graph? How can I find the points of inflection? And how do I know where it's concave up and concave down on the function? So here we go. We're going to practice it. We have to discuss the concavity and the points of inflection. Well, whenever you read points of inflection or concavity, you just need to think that is the second derivative. So get to the second derivative. So right now we're at 4x cubed plus 3x squared minus 6x. I want the second derivative, 12x squared plus 6x minus 6. Well, the way you get points of concavity are just the same way we got our critical numbers. But this is where our second derivative is equal to 0, or where it does not exist. So looking at this, I need to set this to equal to 0 and solve. But first I want to factor out a 6. I get 2x squared plus x minus 1 equals 0. Okay, and I need to factor again. I'm going to do the guess and check on factoring. I know that has to multiply to be 2x squared, and I know these have to be 1. Well, now I just have to determine which one has to be negative. And if I multiply, that gives me a positive 2. That gives me a negative 1, so I'll add to be that positive x. So now I know my possible points of inflection are 1/2 and negative 1. Well, we proceed just like we did with the first derivative test. We draw our number line and mark those values on there. And now we now we test in the second derivative. Plug in negative 2. That's going to be negative. That will be negative, so a negative times a negative is positive. Plug in 0. Negative, positive, negative. Plug in 3, positive, positive. So now, talk about your concavity. We know we're concave up wherever we're positive. So from negative infinity to negative 1, and from 1/2 to infinity. We're concave down on the interval from negative 1 to 1/2. So do we have any points of inflection? Well, that's where it changes concavity. So negative 1 is 1 because I changed from positive to a negative, and 1/2 is 1. So negative 1 and 1/2. Well, how do we get the y values that correspond with them? That would mean you go ahead and plug it into the original problem. And because of time, I'm just going to look that up real fast. Negative 1, negative 2, and 7/16 were the y values. All right, so at this point, I remembered. So I want you to turn in a piece of paper drawing the picture of concavity that fits you. So if you're feeling happy, you'll draw the concave up face. If you're feeling sad, you'll draw the concave down face. So turn that in tomorrow when you come into class first thing. Okay, last example here. If you notice, why am I not erasing? Okay, it's working, kind of. We'll just leave it. Okay, so they've already done the hard work for us. They've given us the second derivative because it was going to be kind of messy to clean up. And at this point, we're just working on concavity. But once again, we need to determine what x can or can't be. So look at the original function, and right away we know x cannot equal plus or minus 2 because those are vertical asymptotes. So I already know I'm going to mark them on my number line. Draw them as vertical asymptotes because I do need a test around them because things can change, but I just won't count them as critical numbers. So now we need to find our possible points of inflection, and I called those critical numbers, sorry, our possible points of inflection, by setting the numerator equal to 0. So 3x squared plus 4 equals 0. So if you solve for that, you get 3x squared equals negative 4. And what's going to happen there when you go to solve that? You're going to get a negative under the radical, which means that top part is never going to be 0. So we actually don't have points of inflection, but we still need to test on our number line because we can still know when the graph is concave up or concave down. So we plug in negative 3. Well, we know if I plug in a negative up there, that top is always going to be positive. If I plug in a negative 3 here, that will be 9, which will be positive as well. If I plug in 0, positive 0, that's negative. And I know if I do positive 3, it's going to be positive. So I know it's concave up from negative infinity to negative 2, and from 2 to infinity, and it's concave down on the interval negative 2 to 2. So do I have a point of inflection at 2 and negative 2? No, you don't, because remember, x, I forgot to write, cannot equal those numbers because those are asymptotes. So there are no points of inflection on this one. So here's just, oh, that slides with it, that's great. So that's how you go about finding concavity and finding points of inflection. So now there's another way you can use the second derivative test where you can test for max and mins. So you use f prime, you find your critical numbers like you normally would in f prime, but then you plug them into f double prime. And if double prime of that critical number equals a positive, then you know it's a min. If f double prime of that critical number equals a negative, then you know it is a max. So we'll go ahead and show you. Oh, and no, if you get the second derivative to equal 0, it won't work. It means you have to go back to the first derivative and do your number line test. So some students are like, well, why do I even care about the second derivative test? Because sometimes it's quicker to hurry and plug it into the second derivative to know if it's a max or min, rather than doing the number line test. So it's just about saving time. So f prime equals negative 12x cubed plus 12x. So I factor out a negative 12x, and I get x squared minus 1. Set that equal to 0. I have the critical numbers of 0 and plus or minus 1. I'm going to take the second derivative. F double prime equals negative 36x squared plus 12. So f double prime of 0, if I plug 0 into there, I get 12, which is positive, so I know 0 is a min. F double prime of 1, well, 1 squared is 1, so negative 36 plus 12 is going to be a negative 24, so that's negative, so that means 1 is a max. If you notice I do negative 1, I get the same thing because of the squared there on the x is negative 24 as well, which is negative. So therefore, I know I have a relative max at 0 and, a relative min at 0 and a relative max at negative 1 and 1 at positive 1. So that's an example of using the second derivative test. So last example right here, we want to find all the x values of a relative maximum and a relative minimum when possible. So the first thing is find your critical numbers, and that's where your first derivative equals 0. So I know my critical numbers are negative 3, negative 1, 0, and 2, because the derivative equals 0. So now I need to know, well, what is g double prime of negative 3? Well, that is 4, so therefore it's positive, which means I'm smiling. So I know that is a min. And all we can do is find the x value. So we know there is a min at negative 3. Make sure you understand that. Okay, so now we need to know, well, what is g double prime of negative 1? That equaled negative 2, so it's negative, so I'm frowning, which means I created a max at the x value, -1. Okay, g of 0, when we get the second derivative, test to equal 0, we can't determine anything. It fails. We don't know what that is. We would need more information to determine that. And our last one we need to look at is g double prime of 2, which equals 3, which is a positive number, which means it's a min, because we're smiling, so we're in a valley, at the x value 2. So there we go for the second derivative test. So that's all of 4-3 is learning how the second derivative tells us what the graph of f is doing, and also how we can test the critical numbers in the second derivative to determine if it's a max or min. We'll see you tomorrow.